Righto, welcome everyone to today's webinar. Now this, I believe, is the 8th of the Ocean Protect webinars. Look, they're continuing to prove extremely popular, which is, great to see. We're really sort of stoked that people give up their time during a work week and a work day to listen to our presenters and discuss various issues in our industry. And this certainly this topic has got a lot of attention, and it's actually great to actually get, I guess, an insight from Craig, who's based in Oregon in the United States of America. So obviously in our industry, we often look within our own borders in Australia for guidance and expertise. But one thing I'd certainly like to encourage us all to do is to look overseas, and particularly in America, where, bioretention systems in particular are very commonplace, fairly similar sort of situation to Australia. And they've obviously done a lot of research and innovation in that space for a long time. And certainly Craig's been a key part of that. So for those who aren't familiar with Craig, Craig is actually a regional regulatory manager at Contech Engineering Solutions. And he works over about 12 states in the central and Rocky Mountain regions of the US. And actually, for people who have got a little bit of time up their sleeve, apologies, Craig, I'm gonna embarrass you, but Craig is actually a very, very successful punk rocker. So I won't go into any more details, but let's just say he shreds like very few others. So pretty excited that he, after I think at the age of about 30, he put down the guitar, at least a little bit, and pursued a career in engineering. And here we are, learning from his expertise and experiences from the States. But before we get into Craig's discussion, just a few little bits of Ocean Protect news, if I can indulge ourselves, if I can work my computer somehow. So you might have seen, if you are, I guess, subscribing to our newsletter, etc. There's been a few little news items of note. So number one is we actually recently installed our 30,000th storm filter in Australia. So we've been putting those in for about 20 years. So yeah, but 30,000 obviously is a huge number, and it's certainly a testament to the hard work and dedication of various Ocean Protect staff. So well done to all involved. You might have, if you're a listener of our Ocean Protect podcast, we recently released our 108th episode with Lorna Parry, who is the co-founder of Underwater Earth. And that was a super chat. And you can listen to all those podcasts on all the podcast platforms like Spotify and iTunes, etc. And if you like webinars, and I suspect you do if you are attending this one, we've got 2 more coming up. Next one is going to be on 30th of September, and that's presented by Daniel Page and Damien Egan. And these guys know their stuff when it comes to gross pollutant traps, particularly the Ocean Save GPT, which is Ocean Protect's latest and greatest gross pollutant trap. But it's a continuous CDS sort of system. So if you'd like to tune in to that one, that's a free webinar. And then the week after that, we've got Ben Penaleric from Blacktown City Council and Griffith University. He's presenting a topic titled "Learning from Ecosystem Management to Overcome Challenges Affecting Vegetative Stormwater Treatment Assets." So that's all I wanted to talk about today. And look, like I said, it gives me great pleasure to hopefully, well, I'm seeing if I can get this to work. Sorry, Craig, if I'm stuffing this up a little bit. It's always a bit of a slow transition somehow. Now, Craig, I think you should be able to take over from me, hopefully, by now. Did you want to try and share your screen?
Let's give it a whirl here.
And look, again, for those who aren't familiar with Craig, Craig's from Contech Engineering Solutions, and he's based in Oregon in the USA, and he's done a lot of work in relation to bioretention systems in the States. And without further ado, so Craig's going to give a presentation. If you have any questions you'd like to ask Craig, please put them in the Q&A panel, which you'll see in the Zoom window, and we'll try to get to all those, as many of those questions as we can, okay? So Craig, without further ado, thanks so much for giving up your time today, and I'll hand over the reins to you.
All right, thank you so much, Brad, for having me here today. I'm excited to talk to everyone, all the stormwater practitioners in Australia, about bioretention and high rate biofiltration and the research and performance updates from the US. And as Brad mentioned, my name is Craig Fairbaugh. I'm a regional regulatory manager for Contech. Before I was a regulatory manager, I was actually a design engineer for about 6 or 7 years, designing stormwater treatment systems and gosh, over 35 states across the United States. I've got a bachelor's in environmental engineering from Portland State, currently wrapping up a master's in environmental and water resources engineering. And surprise, my research interest is in stormwater quality, and particularly synthetic runoff and long-term performance and maintenance demands of stormwater control measures, or SUDs, as I know that you guys refer to them. You know, as a regulatory manager, I cover, as Brad mentioned, about 12 states in the middle of the country, primarily working with city and state agencies on stormwater manuals, updating standards. Obviously, you know, we do manufacture stormwater treatment devices, so to make sure that those are accepted, and to kind of walk through all the technical jargon and make sure that you know, the highest standards for stormwater treatment are being used in those areas. And also, as Brad let the cat out of the bag, you know, I have been to Australia a few times in a former life. I played music for 10 years. And I just really love Australia. You know, been there, gosh, I think 3-4 times. It's hard to remember, but thought I'd include a shot here for fun. Actually had the chance to play the MTV Video Music Awards, I think it was, in 2008, with this band right here, Juliet and the Licks. That's me, second from the left, with a heck of a lot more hair on top of my head and a lot less hair on my face. But we're not here to talk about music today. We are here to talk about bioretention. And here's an agenda, a few things I'm going to be talking about today. We'll talk a little bit about the background on bioretention and some of the challenges we're seeing here in the United States. It sounds like there's some similar challenges going on in Australia. Hopefully there's some helpful information here for you all. We're primarily going to be talking about bioretention media, and I'm going to be using 3 different sources from some really fantastic state agencies, or regulatory agencies from the United States that have been doing a lot of great stormwater work for the past 2 decades. So, you know, they're really experts at what they do. And that's Mile High Flood District in Colorado, the Minnesota Pollution Control Agency, and Washington State Department of Ecology. And we'll look a little bit at bioretention performance and some updates we've had, particularly with high rate biofiltration. And we'll wrap it up with just a couple slides on data gaps and the research that I'm working on and kind of the next steps of what I'm seeing out here for bioretention. And before we get started, I wanted to walk through a few definitions. Stormwater control measures, SCM, is what is commonly used in the US to describe treatment systems. I know that there are different acronyms that are used from region to region, but I'll be speaking my native tongue here, so and using SCM in this presentation. For bioretention, bioretention nomenclature also really varies from region to region, even in the states. From state to state, people use it differently. Urban drainage in Colorado, I work with also known as Mile High Flood District, work with them pretty frequently. They define bioretention as a depressed landscape area designed to capture and filter or infiltrate the water quality capture volume. Many regions will call systems bioretention regardless of whether it has an underdrain or not. Some will use the term biofiltration when there's an underdrain only, but for this presentation, I'll be mostly using the term bioretention. And you can see a little diagram there on the right. Hopefully everyone's familiar with bioretention, what it is, how it works, that's on this webinar. But if you're not, I mean, it's exactly as the definition sounds. It's a depressed landscape basin that's capturing stormwater runoff on top of it and is filtering it through a media and a gravel bed. Sometimes it's infiltrating into the ground. Sometimes it's discharging off site. Sometimes it's doing both. Sometimes it's only discharging off site. And so why all this focus on bioretention? It really is the most common and popular stormwater control measure due to the many benefits achieved when it's designed properly. Pollutant removal, rate and volume control, aesthetic benefits with plants, trees, and vegetation. And it can also benefit local ecology by creating habitat for pollinators and other species, and can even mitigate the heat island effect in dense urban environments. So it's really easy to see why bioretention is so popular. It has so many different benefits. They're difficult to wrap all those benefits into one treatment system. And they've been around for a long time, I think over 20 years at this point. However, after 20 years of implementation, we're still seeing a lot of failures of these systems in the United States. I think you're seeing that in Australia too. And consequently, they're not really functioning as designed. These are systems that are supposed to be removing pollutants from the environment. And if they're failing, they're not really doing their job. And shown here on the right is a bioretention system that was designed with the best intentions, but is now clogged and backing up water at the surface. I believe I borrowed this from the Minnesota Pollution Control Agency, so this is in the Midwest somewhere. And I don't know what the cause of this particular failure was, but there really are multiple failure modes that can occur when designing and constructing bioretention. And even just sourcing the media, and storing it, blending it, there's several points of failure that can really affect your water quality outcomes. And really what an engineer has designed on paper is not always constructed to specification on the site. And oftentimes, sometimes even that specification used in the first place can be inadequate or not detailed enough to avoid these failures. And so this is really a common issue with media sourcing, storing, and blending, as I mentioned, and even installation. My hat's off to contractors that work hard to source and install these systems, but oftentimes it's just simply not done adequately. And I know a misconception here in the States, especially for contractors, is that these are landscape features and are seen, just quite frankly, by some as just a dirt and hole with plants, just kind of a landscaping feature. However, in reality, I like to think of these as, these are really sensitive, decentralized mini wastewater treatment plants that are protecting the environment. And so, further, a lot of the performance data that we have from these systems is from academia level researchers who are experts in how to best construct each variable. And, as a researcher myself, researchers are obviously highly invested in making sure the systems do succeed. So, again, no knock to the contracting community. They do a lot of fantastic work in protecting our receiving waters, but there's just really a gap between the way these systems are installed for research and the data that we see coming out of research and how they're actually sourced and installed in real world settings. So really the central theme of this presentation and from my perspective for bioretention currently is how do we best translate all the great research we have into practice? We have 20 years of research on these systems and we're still seeing so many failures. Why is this happening? And from my perspective, there's really a two-pronged solution here. First, we need to have a thorough and adequate media specification. Without the correct recipe, we're just not going to achieve our desired water quality and design outcomes. You've got to start off with the correct recipe and the correct spec. Otherwise, there's just, again, a lot of failure modes and high likelihood of not achieving water quality outcomes. And you can't just have that recipe and that specification alone for the media and the system. There also has to be a regulatory enforcement mechanism there. If a proper specification isn't required, unfortunately, folks aren't just going to spend time and resources and money on SEMs and SUDs out of the kindness of their own hearts. I wish they would. I certainly would. If I had a ton of money, I would put treatment systems everywhere. But there needs to be some sort of regulatory requirement and adequate oversight in the form of either a plan check review, as-built inspections. There has to be some regulatory enforcement to get these specs actually used in the field and in practice. So a little bit about the sources in this presentation. The Mile High Flood District in Colorado is a renowned agency in the US. The Colorado River alone is responsible for providing drinking water to 40 million people. And the district is currently updating their stormwater criteria manual. I'm a stakeholder in that group that's updating the manual. And as such, they've compiled a bioretention media literature review to kind of update their current spec. And so a lot of the content in the next slides, I'm really just summarizing some of the content there. It's a really great lit review of all the best practices that are out there and was put together by one of the leading water resources consulting agencies in the US, Geosyntec Consultants. So big thanks to Geosyntec for the great work and lit review. I'm really, in these next slides, just a messenger here, bringing you all the highlights of all the fantastic research that was done and their lit review that they put together. I'll also be peppering in some of the lit review with guidance from the Minnesota Pollution Control Agency. MPCA has an online stormwater manual with a similarly thorough lit review of bioretention best practices. And the manual is online, which is a really novel concept. So MPCA can update it in real time whenever new research or best practices are available. Typically, if the manual isn't online, you're waiting 4, 5, 6 years, sometimes longer, for stormwater manuals to be updated. And so a lot of the design information can really be outdated. So can't say enough about this manual, and having it online. As soon as any new research comes out, any best practices, they can update it right away. I use it as a resource for cities and agencies I work with in the United States whenever possible. It's just a fantastic and thorough guide. And I didn't know this when I started working with the state of Minnesota. I'm a native of California. I'm from the West Coast, so wasn't really too familiar with the state when I started doing work in stormwater there. But they're actually known as the land of 10,000 lakes. And to be precise, 14,444 lakes over 10 acres. And unfortunately in Minnesota, a lot of these lakes are impaired for phosphorus and nutrients. So here's a map here on the right, just kind of showing the extent of impaired lakes there in blue, and impaired rivers in red. So they have a lot of impaired waterways for phosphorus. And as we'll see in the slides throughout this presentation, bioretention in the United States really has a known phosphorus leaching problem. And I imagine that's a problem in most jurisdictions around the world, really, if they're all following kind of the same dated specifications. And I bring this up because Minnesota has such a keen eye on phosphorus removal. They're really looking at bioretention media closely because they want to protect their receiving waters from nutrients. And as such, most of the agencies do require 60% removal of total phosphorus, which is a pretty high bar. Washington State Department of Ecology verifies manufactured treatment systems 50%, so this is just a little bit higher, and trying to remove 60% total phosphorus on all stormwater projects. So the Mile High Lit Review, again, will kind of serve as our guide here through bioretention media topics. First, we'll look at gradation and particle size distribution of media. We'll look at organic matter content, homogeny or homogeneity of bioretention media, hydraulic conductivity. We'll look at the loading rate, which can also be seen kind of as a surrogate to pollutant loading and designing for maintenance. And we'll briefly look at recommended bioretention media depth. The table you see on the top right there is the current spec for Mile High Flood District for particle size distribution and gradation of bioretention media. And note that about 80 to 90% of sand is common amongst most specs for bioretention. However, the percent of fines and silts and clays is really that most sensitive variable of concern. And the Lit Review suggests more fine material can promote better nutrient removal and water retention to benefit the plants and growing your vegetation. However, there's really a trade-off where when you're using more fines in the media, it can make the system clog faster. And this is really a common theme I hope that you see as we go through these slides for bioretention, where there may be an advantage to adjusting one component or one variable of the system, one ingredient of the recipe, so to speak, but there's typically an effect on all the other components and ingredients. And there can be disadvantages to other components when you have advantage when you optimize some parts of it. And so this is really one reason why bioretention specifications are so difficult to get right. It's just a delicate balancing act of ingredients. And I just can't ever state this enough. I try and say it in every presentation I give. These really are like mini wastewater treatment plants. They are engineered systems. And so looking at that Mile High Flood District spec in the top right, note the high amount of clays that are allowed currently, up to 17%. I would say the system used that much fine material and was not oversized to prevent frequent maintenance. It would probably end up clogging similarly to that system that we saw earlier. And the Minnesota Pollution Control Agency actually has 6 bioretention blends in their manual, but only 2 blends do they recommend for phosphorus removal, just because nutrients are such a problem for the other 4 blends. They do not recommend them. And so shown on the right is a North Carolina State Bioretention Media Blend, which suggests a lot less fines, only 12% max fines and only 5% max clay content, which, as you can see, is significantly different from the Mile High Flood District recommendation, where they might allow up to 17% of clays in there. So very different results there. Hopefully the district updates that to be a little bit more in line with keeping nutrients out of our receiving waters. Looking at organic matter, Organic matter is really the critical component when we're thinking about nutrient removal and leaching potential if we're leaching nutrients. And a common blend used in the United States, really in a lot of jurisdictions that don't really have thorough recipes for bioretention, is what's called the 60-40 blend. I don't know if you guys have something similar out there in Australia, but it's a really simple spec that's made up of 60% sand and 40% compost. And obviously bioretention needs organic matter to support plant health and retain moisture. However, too much organic matter can lead to that nutrient leaching. And shown on the right is a list of organic matter sources from the lit review. And note that there are disadvantages and advantages columns there. And we'll talk about leachate testing later in the presentation, but to verify that you're not leaching nutrients or harmful chemicals downstream can be really expensive tests to conduct and verify. And that Minnesota Pollution Control Agency mix that they recommend if you do have phosphorus sensitive waters, mix C, recommends to control nutrient leaching. Organic matter should only be 3 to 5% by volume, which is obviously starkly different from 40% compost. And the way that I like to explain this in presentations, just the really simplest way, is to think about, think about a sponge and a tea bag. A tea bag leaches its contents downstream, whereas a sponge will retain any material trying to escape. So we definitely don't want to be tea bags with our bioretention systems and just kind of washing out all this organic matter and nutrients downstream, which can be a big problem and has been a problem here in the United States. The literature review research demonstrated layering different gradations can be beneficial to performance with specific respect to nutrient leaching. I hope you guys are seeing the pattern here, how much of a problem nutrient leaching is for bioretention media. And the research has shown that layering a high conductivity media over a low conductivity media can help retain any leaching nutrients from organic matter. And so nutrients typically leach in the dissolve phase and require more contact time to sorb to active sites in the media. So research has shown in the lit review that choking off flow in a lower conductivity media at the bottom of bioretention is shown to be really effective in removing total phosphorus. Looking at hydraulic conductivity of media, this is arguably, from my perspective as a designer, one of the most important aspects of media specification. It's often used to size a practice. And it's not only the rate at which runoff can pass through the media, but it's also the rate at which pollutant removal has been demonstrated in research. So very important metric here. And in the US for public domain conventional systems, this is typically on the order of about 1 to 12 inches per hour or approximately 25 to 300 millimeters per hour for metric units there. And the lit review from Mile High Flood District notes that a media specification alone can't really determine the conductivity. And this really gets to the point that conductivity in real world storm events, it really fluctuates and is dynamic. There really isn't just one conductivity, obviously, that occurs through media. You have things like vegetation root growth affects conductivity as the roots are growing and decaying. The media can be compacted during insolation. That can significantly affect conductivity, sometimes in a negative fashion. The system can also be partially clogged, which has reduced conductivity. It can be undersized. There's just really a lot of variables that can affect your hydraulic conductivity. And research, no surprise here, the literature review showed an over 3.5 time decrease in conductivity over a 1.5 years of system being in the ground, which is really to be expected. And most jurisdictions do have safety factors to account for those decreases in conductivity. And this research in particular suggested applying a safety factor of 3 to 4 on the hydraulic conductivity to account for eventual clogging over time, which really results in a much larger footprint of the bioretention practice if you want to make sure that you're hitting your design hydraulic conductivity. And just a quick side note that I always have when we're thinking about these long-term water quality studies and we're thinking about things like hydraulic conductivity over a year, 1.5 years, is did the system did the system stop removing pollutants before the hydraulic conductivity start to drop? It's did the drop in hydraulic conductivity? It can be a decent surrogate for solids removal. but you could be leaching nutrients and dissolved constituents far before you see a drop in that hydraulic conductivity. And so I think that's a really important question. When we look at drops in hydraulic conductivity and we think that's the point at which we need maintenance, sometimes we can be leaching and hit breakthrough on nutrients and metals far before that drop in hydraulic conductivity. And I think that's a really important question that I'm hoping research will kind of tackle here in the future. And the research also suggests that field results do not always correlate with the design intent, and that the only true way to know the conductivity of your media is to test the actual site-specific media being used. And that's just kind of common knowledge. Maybe if you're sourcing your sand from a quarry, perhaps they may have tested a batch 6 months ago, a year ago for hydraulic conductivity, but it's really important to understand the hydraulic conductivity of the material that you're sourcing yourself for that project. And at a minimum, it's a best practice to make sure that the media has been batch tested for conductivity. So you know that at least the batch that you're pulling from has been tested and is in specification. And speaking again to the delicate balance of variables at play, on the right there is an excerpt from the MPCA manual, which suggests different conductivities required to remove different pollutants of concern. And note that the MPCA and research suggests media must flow at a really low conductivity, about 1 to 2 inches per hour, or approximately 25 to 50 millimeters per hour to remove nutrients. However, it's also interesting to note at the top there, highlighted, is they have some guidance that says slower infiltration rates actually could clog over time. So just once again, I can't say this enough, it's a very delicate balance to remove nutrients and have a reasonable hydraulic conductivity so the system footprint is not overwhelmingly large. In bioretention systems and all SCMs and such should ideally be sized using that hydraulic conductivity or an infiltration rate. Sometimes people call them different things. Hydraulic loading rate we also use, but sometimes this isn't really known, again, because it's dynamic or just perhaps there just isn't a design criteria provided for that by the local agency. And so kind of in lieu of that, design manuals will recommend sizing a practice based on the size of the contributing drainage area. And Mile High Flood District recommends that bioretention footprints must be at least 2% of the impervious drainage area, which is fairly common in the United States. But some agencies, like the Minnesota Pollution Control Agency, recommend that the footprint must be larger, or 5 to 10% of the contributing impervious drainage area. And this is presumably to be able to meet those phosphorus goals that they have in Minnesota, but also it's just a best practice that I think people are tuning into to minimize the amount of maintenance needed and really prevent the premature failure of these systems. And the lit review research did confirm some of this approach with field data, showing there on the right a system size at 4% of the contributing drainage area in light blue. This had a much higher hydraulic conductivity. You see that decrease over time that we were speaking about. And then you can see the smaller size 0.7% system in green, which demonstrated a much lower conductivity. And media depth is pretty uniform amongst most bioretention specs. It's usually around 18 to 36 inches. And the lit review did demonstrate that increased media bed depth can promote higher removal of dissolved constituents like phosphate and metals. Deeper media beds can also allow for more anoxic conditions, which can help promote removal of nitrogen and denitrification. However, again, there's just really that delicate balance when you start to get into the world of trying to remove nitrogen in these systems and getting anoxic conditions in the very bottom. Anoxic conditions can also promote the release of captured particulate phosphorus into the dissolved phase. And so again, that nutrient leaching problem downstream. And so, it's a really delicate balance if you're trying to remove nitrogen and phosphorus in the same system. Moving on from some of the media specs, the lit review did cover vegetation, and vegetation obviously plays a critical role in bioretention systems. This is pretty commonly known and well researched. And the research in the lit review demonstrated vegetation is critical to remove nitrogen and phosphate. And without vegetation, nutrients can be leached once again. And vegetation does improve conductivity with the root growth and decay, creating macropores as it over time as the roots expand and die. And this phenomenon can also contribute to extending the life cycle of bioretention systems. In one research study, it showed extending the life by 3 to 6 years. And last point on vegetation, it can provide some volume reduction via plant transpiration. I don't know how significant that is compared to infiltration if you're infiltrating below the practice, but there is some volume reduction from plant transpiration. But there's a trade-off there again. It might not be a good idea to jam pack your bioretention system with tons of vegetation. Some of the research might suggest that, hey, more plants, we're going to get better benefits. But if you're thinking, once again, about nutrients and nutrient pollution, if you have a dead plant matter, maybe you have a deciduous plant in there that sheds its leaves, and that can decay on top of the practice and send some nutrients downstream to pollute our receiving waters. So really, it is a delicate balancing act to get all these specifications correct. And mulch is somewhat of an interesting topic. Some folks don't even use mulch in their bioretention systems. Many do. The literature review spoke to mulch removing hydrocarbons. It was showed excellent removal for hydrocarbons and oils and grease. Again, nutrients popping up here again. There is the leaching potential for nutrients from the mulch even. And so the literature review recommended that your mulch, if you are using mulch on top of these practices, that it's free of soil, roots, plant clippings, and debris. And some jurisdictions don't use mulch because they have floating concerns. The mulch during larger storm events and bypass, the mulch will actually float and go downstream, which is obviously not great, especially if there's pollutants that are caught in the mulch. And literature review does discuss the benefits of different kinds of shredded mulch between single, double, or triple shredded. If you're interested in the mulch specification, I recommend taking a look at the literature review itself. But they also do recommend there's some simple floatability tests for mulch if that is a concern. They recommend a really simple test that anybody can do. Put your mulch in a bucket, stir it up, let it sit for 24 hours and see if it floats. Pretty self-explanatory, easy DIY check there. But if folks are using mulch in these systems, I would strongly suggest having some sort of certification if that exists. I know that here in the States, we're fortunate enough to have the Mulch and Soil Council, which does kind of a baseline toxicity test for mulch and makes sure that everything that they supply meets that leaching and toxicity test. There's a link there if you want to learn a little bit more about the Mulch and Soil Council, but that's really helpful to at least have a baseline that the mulch has been verified. And so again, here we are, nutrients. Nutrients have been really a hot topic in the US for the past decade. And so folks have been implementing media additives to reduce nutrient pollution, specifically water treatment residuals, which contain alumina and iron, sometimes just alumina and iron that's sourced on its own. And they've been using these iron additives in Minnesota, especially in sand filters. You can see there pictured on the right, that is a iron enhanced sand filter. But they've also been using these additives in bioretention media as well to remove phosphorus in particular. And they've been pretty successful. There's a lot of great data on this. But again, using this in bioretention media, you've got to pay attention to that balancing act. And while it might be great for removing nutrients, if you have too much iron or alumina in the system, it can actually do too good of a job and take up too much phosphorus and not be bioavailable for the plant. And you can have plants die because of it. If you just think that, hey, iron and alumina are great for removing nutrients, let's put a ton in, it can actually kind of backfire on you and kill the plants. And I don't know if this is a really hot topic in Australia, but I know that biochar, at least for the past 5 or so years, has been a really hot topic at conferences and amongst researchers. And there's a lot of promising research and kind of lab scale data, even some field data out there that shows great results for biochar for multiple constituents and pollutants of interest. But the general consensus with biochar is that there needs to be more research done, especially for sourcing and pyrolyzing to spec. There just remains a lot of challenges with scaling up in the manufacturing processes before it's a viable solution. Moving on from that literature review, the Washington State Department of Ecology, they're kind of in a different position here. They identified the bioretention nutrient problem all the way back in 2013. So they were kind of really at the forefront of identifying this problem. And notably, their bioretention spec still to this day uses 40% compost, which we know leaches nutrients into receiving waters. And as a result of learning this, they studied bioretention media for 8 years to solve this problem, and recently introduced their guidance on using high-performance bioretention soil mixes this last May. So this spec actually is currently available alongside their 60/40 blend. And I wanted to discuss this specification as it really is the best attempt yet that I've seen by a public agency to adequately address nutrient pollution by bioretention and really have a robust spec that's going to perform well over time. And the current guidance from Ecology has been to not use bioretention practices which may discharge to phosphorus-sensitive receiving waters, which at first thought makes sense. You know, this really complicated blend, it may not need to be used everywhere. However, personally, I would really counter this notion. While some waters in the US are definitely identified from a regulatory perspective of being impaired by phosphorus, I would suggest that all receiving waters are sensitive to phosphorus. Meaning that if we keep using systems that leach nutrients and are exporting phosphorus in our downstream waters, won't we just make those waters impaired at some point? You know, and just as engineers, you know, personally, I feel we should be designing proactively to solve nutrient problems. You know, once we have things like harmful algae blooms and eutrophication in our lakes and rivers, it's extremely difficult to remove nutrients at that point, and also really costly and sometimes just flat out infeasible. And in Ecology's new blend, they recommend 3 types of high performance media blends, and each blend targets different pollutants. However, really the point, we're not going to go into this into a lot of detail. The link is on the slide before if you'd like to take a look. A lot of great work done by the Department of Ecology. However, just really the point of showing these blends is the extensive amount of testing and quality control that must be achieved to meet this specification. And Ecology has come up with a really great recipe. It seems to address nutrient pollution pretty well. It's been tested in the lab, and there is field testing that is being done right now and should be completed soon. But we're just going to look at type 3 as this is their most robust recommendation that is designed to remove solids, dissolved metals, and phosphorus. And as they note there in that table, achieving additional LID objectives and water quality objectives. And the type 3 blend recommends a filtration rate of about 300 millimeters per hour with 18 inches of high performance mix seen there in kind of the tan color. And that's comprised of 70% sand, 20% coconut coir, and 10% biochar. And then followed by that 18 inches is a 12-inch polishing layer comprised of 90% sand, 7.5% alumina, and 2.5% iron. And then on top of it, to really just promote plant growth, I believe, that type 3 blend has 2 inches of coarse compost on top of the media. And the big question my colleagues and I have about the spec is how will this actually be implemented and enforced? It's a great effort and a fantastic recipe put together by Ecology, but there's a long list of laboratory verification that must be achieved. And you know, it could be difficult to show that all of these materials are sourced, you know, passing all the laboratory tests and meeting the specification they're recommending. And for example, I took some excerpts out of the new guidance here, and each media component requires leachate testing for nitrate, nitrite, total, and orthophosphorus, and copper. So 3 separate leachate tests, potentially 4 there. I don't know. I'll be honest, I don't know if there's a separate test that need to be run for total and orthophosphorus. I would imagine so. You know, so there's a lot of questions here. Similar toxicity tests that we here at Contech have run on our media can cost approximately, you know, somewhere around $700 to $1,000 per sample. So, you know, trying to meet this spec and verifying all these different components can, quite frankly, just be really costly. And secondly, you know, we have questions about who will be checking all of this data. You know, the manufacturers and the suppliers may test this stuff periodically. However, Ecology does suggest, and I would agree with them, that the contractor verify the specific batch meets specification. You know, there's always that time component of when something has actually been checked for verification. And regarding the whole process of plan check review, is the engineer or the city checking to make sure the components were tested to meet spec? Who's checking to make sure the installation is to spec? All of this verification that the materials are correct would likely require more billable hours from the engineer. I would likely require more resources from the city and the plan check reviewers, and additional things to think about. This is really complicated stuff, and understanding all of these leachate tests could result in extra training required for engineers, extra training for the city and the plan check reviewers to understand all the results of all this laboratory testing. And the coconut core similarly requires leachate testing and also verification for compost methods. I'm going to fly through these pretty quickly. They're all pretty similar. The biochar has the most extensive testing required with leachate testing. They also require metals testing for, arsenic, cadmium, lead, mercury. I always pronounce this incorrectly, molybdenum. We'll just pass on that one. Nickel, selenium, and zinc. They also have some leachate testing for PAHs, dioxins, furans, cation exchange capacity testing, some gradation to make sure you have the gradation, correct gradation is being used. It's really a doozy of lab testing requirements, a really long list. And for the aluminum and iron, they also have the leachate testing requirements in addition to some gradation and bulk density testing. Pretty similar between the two. And Ecology does recommend a bioretention media blending, delivery, protection, and placement plan be created and reviewed by the engineer, which is a good start. And there's still some questions though. Is the city going to be checking this plan and rejecting it if it doesn't meet the spec? How will this increase billable hours for the engineer and ultimately the cost of the bioretention system? And does the city have the resources to adequately check the media specs for every single bioretention project? This is a spec in Washington State. Just thinking about Seattle alone, that's a very large city with millions of people, the metro area. I don't know off the top of my head how many millions of people there are, but that means a lot of development and a lot of bioretention systems. This is a gargantuan effort. I applaud upping the bioretention spec to something so robust, but it's going to be interesting to see how it rolls out in future manuals and stormwater permits. And this is where Contech and Ocean Protect's high-rate biofiltration systems, filtera, really shines. Filtera, it's a manufactured high-rate biofiltration system, and it has over 20 years of R&D baked into it. And as the slide says, it's a pre-engineered, pre-packaged stormwater biofiltration treatment system. And it was really designed to optimize all those public domain components in order to reliably achieve long-term pollutant reduction at significantly higher loading rates. And so, namely, our R&D team figured out how to fix a lot of those common flaws with bioretention and also increase the loading rate and shrink the size. Our team, we have a dedicated lab in Virginia that has been working on this for literally 20 years exclusively on bioretention medias and optimizing blends. It's starkly different, from city and state agencies and local practitioners who just don't have those resources to focus this intensely on a stormwater treatment system. And our latest approval in the United States has filtera approved to remove TSS at up to 175 inches per hour, or nearly 4,500 millimeters per hour. So a lot smaller of a system can be used to remove our total suspended solids. And yes, I've been talking a lot about nutrient pollution, probably because I work so much with the Minnesota Pollution Control Agency, but it also just is a really big concern with bioretention in the United States. And yes, filtera has specifically been tested and verified for total phosphorus removal through a year-long field monitoring study with the Washington State Department of Ecology. And shown here is the test site from that monitoring campaign in the state of Washington. And note there on the left, that robust vegetation in the filtera system. Really impressive growth in such a small footprint. It's still shocking to me to this day to see such a robust tree growing out of such a small system. And it's really of note that the system was tested specifically in a phosphorus impaired watershed. That's Lake Whatcom in Washington there on the right. which is impaired for phosphorus and listed on the 303D list, and I believe has a TMDL for it as well. I'm not 100% sure about that, but it is impaired for phosphorus, and the system was tested in that region. And that photo there is actually one of my stormwater consultants in Washington. That's his kayak. And he really loves going out in this lake, and is obviously super proud to supply filtera in this region, and supply a treatment system that helps protect Lake Whatcom. And so moving into some of the bioretention performance updates. So I don't know if you guys are aware of this. Speaking with Brad a little bit before the call, it sounds like a lot of people may not know about this, but there is something called the International StormwaterBmp database. I highly recommend, if you're interested in performance of stormwater control measures and SUDs, taking a look at it. They've expanded their categories. I don't know off the top of my head, but I want to say they have maybe 15 to 20 different categories of SCMs and SUDs in there. And I believe over 900, maybe 1,000 field monitoring studies in there. So it's got a ton of data. And they've recently updated. Every couple of years, they put out their summary statistics. And in 2020, they just put it out, and this is really a big deal for Contech and for high rate biofiltration. This is the first year they actually had that as a category of SCM or SUDs, and they have an actual high rate biofiltration category. And as you would imagine, as a manufacturer, manufacturing these high rate biofiltration systems, we always get the question, how does filtera compare to conventional bioretention? We have robust data, which always helps, but it's really nice to have this included in a great third-party, highly respected database, to be able to really compare side by side some of the performance. And I do want to mention, as the regulatory guy inside of me, the BMP database is not a perfect representation of all stormwater control measures. All these systems were tested on different sites under different protocols. I wish they were all tested using the same protocol, but that is a whole different presentation and something we're working on in the United States to get protocols for both manufactured and public domain devices. But it's just to say that, different sites, different protocols, that stuff can really skew your water quality results one way or another. But however, I still really do hats off to the International StormwaterBmp database and the Water Research Foundation for putting this together, because it is a great high-level reference of how these systems generally work and how they perform from a water quality standpoint. And one more note here before we get into a couple of slides of data. All 5 field studies that are high rate biofiltration in these next 2 slides are filtera high rate biofiltration. So here's the summary statistics for total suspended solids, with bioretention representing, with BR there on the left representing bioretention, and HRBF there on the right representing high rate biofiltration and all 5 filtera studies. And note that the influent concentration is on the left in light gray, and the effluent concentration is on the right in dark gray. And as expected, both these systems are doing a great job with total suspended solids. We know that conventional bioretention can do a good job at just removing solids. And moving on to phosphorus, much different story here. Again, I hope you guys are seeing the pattern here with bioretention and the nutrient problem. There on the left in the red shaded box, bioretention there, and BR, I believe the BI and the BS are grass swales and grass strips. I forget the order, but that's not the point. The point is they're all showing total phosphorus export. And so you can see that the effluent dark gray column is significantly higher than the left. And so they're really, as we've been talking about in multiple slides, here it all is in one slide. These systems have an issue with leaching nutrients, likely due to all the organic matter and compost being used. Really nice for us for filtera. Really easy way to compile all of our data there on total phosphorus. HRBF showing all 5 filtera studies with positive total phosphorus removal there on the right. So I think that's all of my content for today on bioretention media and a little bit about filtera high rate biofiltration and some data updates. And this last chunk of content here is a plug for some of my master's research and the stuff I'm interested in. So in addition to challenges with bioretention media specifications and nutrient pollution, there's really a gap here in the United States in testing protocols to see how long these systems perform under typical stormwater conditions. Mass capacity testing protocols exist in the United States for manufactured devices, but they often don't use all the sticky, nasty stuff like oil and organics that are found in real stormwater. So it's not really representative of field conditions and how these systems are actually performing. And so due to COVID, I ended up actually setting up research in my garage, affectionately termed the Garagetory. I didn't think it was a great idea to be going into my university and doing research, and my bet was correct, as the university has been mostly closed due to COVID. So long story short, I've been researching and running a lot of water quality trials in my garage with all my equipment and pumps and flow meters. And I'm testing both conventional and high rate biofilters with oil and organics to see if we can better understand long-term performance and what makes these systems clog and fail. I really wish I had a water quality lab in my garage. I do not have that. I actually do go into my office. We have a giant laboratory there where I can perform all the suspended solids samples. And again, I'll fly through this slide as quick as I can. Protocols in the US are currently just really only using inorganic sediment for mass capacity testing. So I tested it with inorganic sediment and then also with the addition of oil and organics. No surprise, the systems clog faster when you're adding oil and organics. I have about another month or so of testing, but perhaps if this is of interest to the Australian stormwater community, I'd be happy to come back and discuss my findings and see what kind of implications this has for bioretention and high rate biofiltration. And just kind of wrapping all of that up, thanks for everyone for joining today. I hope this is useful information. Just some conclusions here. U.S. public agencies are taking steps to improve bioretention specifications. The QC, the lab costs, enforcement, and oversight will be a challenge, though. That's going to be a difficult task to get over. filtera high rate biofiltration has proven pollutant removal performance in the field. There's some complicated media spec work, procurement, enforcement, installation issues that we've tackled and are minimized or just outright eliminated. And last point, more data really is needed on long-term performance and maintenance triggers. Hopefully I'll have some answers on that with my research and maybe be coming back to talk to you all about that. But with that, hopefully we have some time here for some questions. I went a little bit long. I do apologize for that.
Look, Craig, I don't think anyone's complaining. I think that was a very interesting presentation, and look at the questions are certainly coming thick and fast. And just as a reminder, if you do have questions, please put them in the Q&A section. If we don't get your question today, obviously Craig's email address and contact number is there as well. So if you want to contact Craig directly, you're welcome to. A few people have asked whether they can get a copy of the presentation slides. Yeah, all the slides of all our webinars are on the Ocean Protect website and under the webinars tab. So just head to there. Probably by tomorrow they should be up there. And look, I'll go through first in best dress basically. So very early on, we had a couple of questions from two staff from Blacktown City Council. First was Ben Peneleric. Ben asks Craig, what research shows that increased organic matter content leads to nutrient leaching? How much research has demonstrated this, and of it, were there limitations in the methodology? E.g., research was only undertaken at the early stages of the system life and didn't seek to understand if it reduces over time.
Benjamin, that's a fantastic question. Like I mentioned in the presentation, Department of Ecology, Washington State Department of Ecology identified this in 2013, and they had a good amount of research was conducted on this. And I would, if you reach out to me offline, I'd be happy to point you in the right direction. But you can go to their pages. They have extensive research and all documentation, all the research that led, to their findings on nutrient pollution. And if you go and check out their high performance bioretention soil media guidance, there is a link in the slides. As Brad mentioned, the slides will be available. They do have a little synopsis in there, and I believe that what they found is that it leaches, the systems were leaching phosphorus and dissolved copper for the first 2 years, and then it starts to decline after that. I think there's more information if you follow all the links and all the studies. They studied this, they found out the problem in 2013, and they've been monitoring it and trying to fix it ever since. So there's a lot of data and a lot of really thorough reports if you follow those web links.
Cool. Next one was from Mark Liebman. Mark says, great work, Craig. Thanks for sharing. Any thoughts on how Minnesota rainfall patterns influence their specification? We are, and that's Mark's from Blacktown City Council, we are moving towards specifying 3 to 5% organic matter content by mass, not volume, as we have much less frequent rainfall, presumably. Any comments? So I'm not sure if you're familiar with Blacktown rainfall patterns, Craig, but it's about 700 millimeters a year on average. Rains, I guess, most of the year, I guess.
Okay, yeah, I mean, that's a great question, and something that I think that folks are trying to tackle here in the United States, how do we piece together all this data from different rainfall regions? I think this is something that's actively being worked on. And the two examples I did use, so Colorado has very different rainfall patterns. They only receive, their water quality storm is about a ½ inch. And I believe receive like 15 inches of rainfall annually, where Minnesota does receive about double of that, and their stormwater design storm is about double that as well. But I think there's always two things to think about when you're thinking about sizing the system and rainfall patterns. We're looking primarily at the pollutant load that's coming off the site. So I think this is a question that I think is very difficult to answer live, but I would suggest that really focusing on the pollutant load is what to identify, and the rainfall and the amount of water coming in is kind of a separate metric.
Cool. Ben asks a second question. What do you see as the best way to remedy poor hydraulic conductivity? What is too low? What is too high? And what is the best, e.g. most practical and cost-effective way to bring it into a desired range?
That's a tough question, a great one. For things like sand filters, this is pretty heavily researched, and just scraping off the first couple inches, we'll get a majority of your particulate stuff that's clogging the system. For bioretention systems, it really depends on the mode of failure. If it was constructed properly, if it's using mulch, it really depends on all these different variables. Sometimes, like with filtera bioretention, Brad, as I'm sure you've spoken with folks about, the mulch does a great job at removing all the coarse material, and you can just replace the mulch. Similarly, for some bioretention systems that use mulch, if they have a correct mulch spec, if they don't, sometimes just scraping off the top couple inches can refresh the system. But again, there's so many failure modes, it's really tough to answer that question. A lot of times compaction can be an issue. Maybe there's too much ponding on top of the system. Maybe there's 18 inches, 24 inches of ponding for bypass on top of the system that compacted it. And in that case, the bioretention, you could need to replace the whole media section.
You mentioned that mulch, and obviously that's a feature of filtera bioretention systems, to have that mulch layer on the surface to protect the filter media. Is that something that's actually utilized for just conventional bioretention systems as well, having a mulch layer on the surface?
It's really hit or miss. Some jurisdictions I work with do require mulch, and some don't. The conventional system that I'm testing right now in my garageatory, they actually don't require mulch. But knowing that mulch can work well, I did follow their mulch guidelines and procured a mulch that meets their spec. So it's really hit or miss across. I think most people's biggest concern is the mulch floating and kind of tackling that issue with conventional systems.
Cool. A question from Craig Norton. Does the filter media pull out the phosphorus directly, or is it targeting the fine sediments that phosphorus can attach to?
That's a fantastic question. So I would say both. Filtration systems like bioretention, if they're designed correctly, they can remove some pretty small sediments. And of course, as Craig suggested here, there is a higher absorption capacity on your smaller clay particles that are coming into the system. So if we're removing those, we're removing a lot of the particulate phosphorus that's attached to it. But the whole point is, depending on, that's why folks are looking into some of those iron and alumina additives, is because that will actually sorb and pull out dissolved phosphorus out of solution and bind it to the sediment or the iron or the alumina particle. So a little bit of both, I would say, depending on your media.
Now, next question was from Kathy Kinsey, and she asks, has there been any investigation regarding the role of mycorrhizal fungi in bioretention media?
Absolutely. I don't have, I don't have a summary of that off the top of my head, but obviously there's a lot of important roles played by all the microbiology in the root zone. I will say that some of my colleagues, Mindy Hills, who is one of our leading researchers at Filtera here in the United States, Jim Lenhart, Brad, obviously they did write a fantastic paper on the microbiology of bioretention systems. I believe it was presented at American Society of Civil Engineers Congress. And so if you're interested in that and in the role of microbiology and bioretention, they have a fantastic paper they wrote about it. I'd be happy to share that link.
Yeah, it's interesting this question's come up because I'm actually hoping to get Mindy to present exactly that paper, it's called the role of microbiology in bioretention systems. So I actually reached out to Mindy literally yesterday. So hopefully she's going to be available to give a talk on this very topic. So thanks for the question, Kathy. Next one was from Alexander Orenson. Any issues with filtera systems or other water-wise streetscape bioretention systems with clogging up from fine silt and sediments? If so, how can they be maintained without harming the tree?
That's a good question. I wish that Filtera and more systems had more particle size distribution for the influence, to particularly answer these questions. But I will say, I think it's fairly common knowledge. If you have fine sediment, whether it's Filtera, whether it's a sand filter, whether it's bioretention, that will clog a system faster. So if you have a site that has a high amount of fines, you want to take that into consideration. But the benefit of Filtera is obviously we have that top layer of mulch, that will remove a lot of your coarser sediment and kind of protect your pore spaces from clogging with the fine sediments below it.
Yeah, and obviously it's quite easy to remove that mulch without doing any damage to the tree.
Absolutely.
Craig Norton asks, have biofilms been looked at in bioretention systems? Permanent submerged zones may promote them.
That's a good question. I'll be honest. I don't know that I've seen much research on biofilms in submerged systems, but I would suggest a good place to look. Dr. Bill Hunt does a lot of work with the internal water storage zones and those kind of submerged zones for removing nitrogen. He's out of North Carolina State University and is one of the leading researchers on bioretention in the country. I would suggest looking at some of his research and see if there's anything on biofilms there.
Cool. There's another question from Mark Liebman. Do you have any thoughts on length? Do you have any thoughts on length of studies and how this influences findings? Typical monitoring is for less than 12 months, and so it might capture leaching in the first year, but once the system's settled down and leaching stops, if it does at all, after the first year, if it is still an issue.
Yeah, that's a great question. As I mentioned previously, Department of Ecology did identify that this was an issue for 2 years for both nutrients and copper. I didn't speak to dissolved copper, but they found that the systems were also leaching dissolved copper, which is a big issue in the Pacific Northwest. We have sensitive aquatic life, salmon, that's harmful to. So at least for the 2 years, they did see significant leaching, and then there was a decline after that. I didn't look at the specific rate of decline, but it does decline after those first couple years. But from a load basis, I think it's significant enough to where they're trying to implement this new blend.
Cool. A lot of comments coming through about just thanking you for the time and the excellent presentation, Craig. But the final question I see on my list, and so if you have a question you want to ask Craig before we wrap it up, please post it now. But the final one seems to be from Murray Powell, who's never short of something to say in our industry in Australia, Craig. But Murray asks, for some coastal systems where phosphorus is not a target pollutant, but metals and hydrocarbons are, we should be using more mulch, right?
Research would suggest yes. Mulch does a great job at removing hydrocarbons, oil and grease, all the nasty stuff on top of your system, which can make it last longer. If you have to remove the mulch, that's fairly easy to do. As the gentleman mentioned earlier, you don't have to damage the vegetation. And as far as metals go, if you're just removing, that's really a site-specific question. If you're just looking to remove your particulate metals, mulch can do a great job. Depending on the kind of mulch, if it's spec'd correctly, can do a great job at removing your particulate metals. Of course, it gets into more complex chemistry. As the system ages, you have different pHs and solid oxygen conditions. That captured particulate metals can transform into dissolved, and then it gets into your media. But I mean, definitely it can't hurt by trapping more of the particulate stuff up top. And if you perform active maintenance and maintain the mulch frequently, maybe you'll prevent it from transforming. So big yes for metals and hydrocarbons.
Big yes. And look, and a big thank you for your time today, Craig. That was a fantastic presentation. There was so much content there, and you've done it well to wrap it up in an hour. So well done. You're obviously a master of timing as well. You've done
I went a little
well.
over. I appreciate all the kind words, though, sir.
But yeah, look, from my perspective, it was a wonderful and really informative chat. If anyone would like to reach out to Craig and ask him anything else or discuss further, his obviously contact details are on the screen now. If you'd like to get a copy of Craig's slides, we'll like I said before, it'll be under the on the Ocean Protect website under the webinars page, and we'll have a copy of the slides and a recording of the webinar as well. So if you want to flick it around to any of your colleagues, etc., you're welcome to do so. And look, without further ado, again, thanks to Craig for his time today. Thank you everyone for attending. It was another great turnout for the webinar today. A reminder, we've got 2 more webinars coming up in the next few weeks. So if you want to register or find out more about that, jump on the Ocean Protect website under the webinars tab. But again, thanks everyone for attending. And again, Craig, thanks for a wonderful presentation. Well done. I'm hoping you're going to come back for a second appearance.
I'd be happy to. Yeah, no, thanks so much for having me, Brad. Happy to speak with you guys anytime.
Cool. Thanks, Craig. Thanks, everyone. Enjoy the rest of your day.
Thanks, everybody. Appreciate it.